All right. Good morning or good afternoon to some of you. Thank you for attending the QIC webinar. My name is Ali Bayat. I'm a faculty member at the University of Alberta and director of QIC. So I'm going to be the moderator for today's webinar. The topic is best practices for geotechnical reports, GDRs and GBRs on underground project by Dani Delaloye. Before we dive into the webinar, so QIC basically webinar is part of QIC Academy. That's Canadian Underground Infrastructure Innovation Center. It's the education and research center at the University of Alberta. And we focus basically, QIC Academy's goal is to focus on education, including these webinars or in-person events on different aspects of underground infrastructure. Webinar series is basically an offering. It's in the year 4, I believe. It's every month on third Thursday of each month at 11 basically a.m. Mountain Time. We have a team or educational committee actively works on putting the topics around these webinars, trying to basically cover the interesting things or the problems that we believe industry is facing. Our 2026 summit is approaching March 3rd to 5th. It's going to be in Mississauga. Again, a 3-day event. Day 1 is going to be on geotechnical engineering on different aspects of underground infrastructure. Day 2 is tunneling and micro tunneling, and day 3 is on directional drilling. So for those of you who are interested, check it. The agenda actually is impressive. Like, this was the Geotech committee putting this agenda together, the depths and the diversity of speakers there. Take a look at that program, and if you have the chance, I encourage you to attend the basically spring summit. The fall summit is going to be this year in Vancouver, September 15 and 16. Committees are working on the agenda, and that one should be ready around in April. Before I introduce our speaker, I just want to acknowledge our 2026 webinar series sponsor is Ackerman. So they are the sponsor for this year's webinar. So we appreciate the support of Ackerman for this series. So I'm just going to quickly introduce. Dani is the North American Tunnel Practice Lead and a principal engineer and project manager with Mott MacDonald, managing and leading the delivery of projects varying in complexity from small trenchless job to large-scale multidisciplinary transit projects. Her technical expertise ranges from the planning and leading fieldwork assignment through technical design and coordination to site condition surveys and inspection. She has worked on a broad range of tunneling, underground, and trenchless projects from pre-feasibility to detailed design phases through to construction oversight. She completed her geological engineering master's degree with a specialization in geotechnical and geomechanical engineering and a focus on underground construction. She has worked across sectors including transportation, mining, water and wastewater, and energy projects. Thank you, Dani, for being with us. And with that, I'll pass it to you.
Thanks, Ali. Thanks so much, everyone, for having me. So today I'll be talking, like Ali said, about best practices for geotechnical reports, focusing in mostly on geotechnical data reports and geotechnical baseline reports. We'll talk a little bit about what sorts of things should go into these reports, how we can set good baselines, going through a couple different baseline examples, and some of the key differences between geotechnical data reports and geotechnical baseline reports. I want to preface this discussion by saying, like Ali said, my background is primarily in tunnel engineering and large-scale tunnel projects, although I have worked on smaller projects like HDD and micro-tunneling projects. And my bias is also to the rock mechanics and rock engineering side of things, although I've worked on lots of soil projects as well. So a lot of this, I'll be talking about tunneling projects, but these types of geotechnical data reports and geotechnical baseline reports apply to other sorts of underground projects as well. So why are we talking about this related to underground projects? Well, underground projects are inherently different and more risky than other types of construction projects. This is because the ground everywhere is rarely consistent. Geological conditions can vary significantly across project sites, especially when we're talking about long infrastructure projects, long linear infrastructure projects, which tunnels and other types of HDD or microtunneling projects are. The other challenge with these types of projects is they only have one construction heading typically. So if your process is stopped, if it gets delayed, everything on your project stops. It's not like constructing a building or something at surface where if one area gets delayed, you can move and reallocate resource at another part of the projects. Some other things that we need to consider for underground projects are that the methods of construction are different depending on the subsurface conditions. And the behavior of the ground itself can actually vary depending on the construction method you select. And the last thing is that unexpected conditions, so things that we aren't expecting, can have a very significant impact on our projects. I can't stress this enough. And last but not least, one of the themes you'll see coming through in this presentation is that construction contractors, the people actually building the work, did not accept risk. They price it. So that kind of feeds into our understanding of how we're developing our geotechnical data reports and our baseline reports. Now, when we talk about uncertainty in underground projects, uh, we like to break it into kind of three different categories. There's the things that we know. Things on projects that are set that we have a very good understanding of. So on a tunneling project, this might be the alignment or depth of the tunnel. We might have a good basic understanding of the geology of the area or past experience in the rock type. There are also things we know we don't know. So these are more specific things that we can get further information on through investigations, but things like intact and rock mass parameters, structural features, so our fracture frequency, information on the joint sets, their spacing, their orientation, the general characterization of the area, potentially things like in situ stress or time-dependent behavior of the rock. And then there's also things we don't know that we don't know. So these are risks that are uncertain on the project. So things we might not be expecting, geological anomalies, discrete hazards, things like an unmapped fault in the area could be something you would put into that unknown category. So when we're developing our geotechnical data reports and baseline reports, we're trying to kind of categorize all these different things in those reports and develop our understanding around them. And as we develop these reports, we want to be thinking about the stages of our projects as well. So a typical underground project evolves from concept and feasibility study through preliminary design onto detailed design and then into construction. So at that concept feasibility stage, you're looking more at initial desktop study information, initial assessments of the geotechnical conditions, moving into potentially some field walkovers, and then your stage one investigation, which are informing your preliminary geotechnical data report and maybe an interpretive report. And then through your detailed design, you may be doing further site investigation programs, which inform your final geotechnical data report, as well as interpretive reports and your geotechnical baseline report. So let's dive into each of those stages in a little bit more detail and what they entail and what sorts of information you can collect. So at the desktop study stage, so at our preliminary kind of concept level of the project, we're typically looking at publicly or potentially privately held information, including historical investigations. So are there boreholes or investigation data from nearby projects? Are there past project experience in the area from construction? Are there regional geological maps? This could include bedrock geology maps, surficial geology maps. Historical air photos of the area can also be really helpful. Today, often we use Google Earth or other online data sets to review the area, looking for things like seismic hazards or other slope stability hazards within the area, and also identifying areas of interest. So things like previous archaeological use, environmentally sensitive area, or potentially historic site use. So was there something that could have caused contamination on that site, like an old tannery or a gas station or something like that? That information gets compiled typically into a desktop study report, providing the basis of the initial assessment on the project. As the project progresses, we might then move into some field mapping and site walkovers. So this helps get us a better understanding of the project area, looking at things like, is there nearby infrastructure? Are there overhead power lines that could potentially limit where we can do site investigation? Are there sensitive buildings that we need to assess in more detail? Are there access constraints to the area? So is there ways in and out if we were planning a site investigation program that we might want to be aware of? Are there geohazards? Are there slope stability issues that we can identify in a walkover? Are there potentially cracks in the ground? Um, we can also undertake geological mapping of any exposed outcrops. So that's that photo on the right there is some geological mapping I was doing up on a project in northern BC, collecting information about the geological conditions, but also the jointing, the rock mass conditions, identifying any lineaments or faults we might see. And then also selecting locations for future investigations, so potentially boreholes, geophysics. In the early stages of a project, we also might look to collect remote sensing data. So this could be LiDAR data, photogrammetry, drone footage, satellite data. This sort of data can be collected from the air, from mobile terrestrial LiDAR data, from static terrestrial, and we can use this to help develop our topography models, help us with site characterization. These days, we can actually pull off rock mass mapping data from LiDAR data and geotechnical information, orientations, persistence of joints, and those sorts of things. So that data can be useful at the early planning stages of the project and throughout the project lifecycle. Then we move into our intrusive site investigation methods. So this could be test pits and trenches, excavating the top few meters of soil, which can give us information on the stratigraphy of those upper layers. Also is very useful for identifying cobbles and boulders, size and distribution. But test pits themselves are quite limited in depth. We also might use things like geophysical surveys. There's various methods of these available. I'm not going to go into those in detail. And then boreholes. So this would be your soil drilling, rock drilling, which allows for sampling, but also in situ testing, things like CPTs, SPTs, in situ stress testing, etc. And also collecting groundwater information. So let's take a step back and think about an underground project and what sorts of information we need to design and construct the project. Well, we need information on the subsurface conditions and to allow us to characterize the ground. So information on the soil and rock types, their properties, the condition and stratigraphy, any obstructions we might encounter. So this could be cobbles and boulders, but it could also be man-made materials, infill, old bridge piers, tiebacks from adjacent buildings, groundwater information, so information on the groundwater table elevation, the permeability of the ground, potential groundwater flows, and other potential risks of the site area. So we talked about environmental information. So is there contamination, either naturally occurring or from previous man-made activities? There's a lot of geotechnical parameters for tunnel design that we need, so I'm not going to go through each of these in a lot of detail, but for soil, there's lots of different information we need to collect. For rock, there is, for the rock mass, for the things like groundwater and environmental that we talked about. And we get this from both that different site investigation methods we talked about before, but also from in situ testing and lab testing of samples. So for example, we want to understand rock mass conditions, so the strength and quality of the rock mass. Why do we care about this? Well, this is an input into our assessment of the rock mass behavior, which allows us to understand how we're going to excavate or support the rock mass, and then also informs the construction methods and support we decide upon. And we can get this information from field mapping, from core logging, from lab and in situ testing. On the soil side of things, for tunneling, we often want to understand the clogging potential of the tunnel boring machine. So we can get this sort of information from Atterberg limit testing. So there's different methods of testing that we want to undertake in our geotechnical data collection to inform the way with which we design and construct our tunnel. Again, grain size distribution, this is another important soil parameter that we obtain through sieve testing, and this informs our TBM type selection. Presence of cobbles and boulders can be very critical for different types of projects. So it can inform our construction method. They can have significant delays on projects. So we want to know if they are occurring. We can get this from past project experience as well, from test pits, from geophysical understanding, and from potentially from boreholes, but it's a lot harder to get a good understanding of the distribution in cobbles and boulders from boreholes. Again, with my tunneling hat on, abrasivity can cause significant tool wear if the abrasivity of the rock or soil is quite high. So this is another thing that during our investigation program, we want to get an understanding of, and it typically obtained through laboratory testing or petrographic analysis of the materials. In situ stress, again, can have a significant impact on our projects. We can obtain information on the in situ stress conditions from in situ testing, pressure meter tests, overcoring, or from past project experience in the area if it's available. Mineralogy is also important to understand as they can have a detrimental impact on excavation stability, with swelling minerals potentially negatively impacting our excavations. Silica dust is also a significant health and safety risk, so we want to know the degree of which silica material we have in our rock. So we can obtain this information through petrographic analysis or XRD testing of our materials. Another significant risk on tunneling projects and underground projects is groundwater. So high inflows can have significant delays. We need to know what the groundwater conditions will be to inform the method we select for construction, but also how to plan our means and methods of handling that water. Again, we get this through in situ testing, potentially packer testing, or other types of in situ groundwater testing, from installing monitoring wells, piezometers, and sometimes we have to wait through to construction to do forward probing during excavation. So all this information that we collected gets summarized within the Geotechnical Data Report. So the Geotechnical Data Report should compile all the raw testing data and results. It's meant to be the single comprehensive reference for the engineers, for the designers, and the contractors on the projects. And as we talked about, projects can span a significant amount of time. So from that preliminary design through detailed design, maybe weeks, maybe months, but as often years. So your geotechnical data report, being the single source of truth for your geotechnical data, may have multiple appendices as it evolves over the years. Best practice is for that geotechnical data report to be included as part of the contract documents for your project, and for the contractor to be provided reliance on that data, which means the contractor can rely on the correctness of that data. Your geotechnical data report should not include any interpretation. So again, it just puts all the data from that investigation that you've done together in one place. Typically, it's structured with first the background information, so information on the geological setting of your area, then into any investigation details, so how many boreholes were done, geophysics, what sort of tests were done, into your in situ testing information, and then the compilation of all the data from your field and lab testing. So this can include things like your test pit logs, your piezometer installation logs, water level measurements, any in situ testing results, so your CPTs, SPTs, pressure meter tests, any groundwater in situ testing, other in situ stress testing, any individual lab testing sheets, photos of soil samples, photos of your rock core, geochemical testing results, any soil and rock mapping sheets. So anything that was data that was collected for your project, all compiled into one spot. Now, let's start talking about baseline reports. So geotechnical reports traditionally, and I'm talking traditionally being back in the 1960s or 1970s, contained clauses like the following. The contractor may encounter a large quantity of boulders when tunneling, which can vary in size from 10 centimeters to 10 meters, and in unconfined compressive strength from 1 to 400 MPa. Or something like the shaft excavation in fine sand and silt for shaft A may require dewatering. Or groundwater infiltration into the tunnel may vary from several hundred liters per minute to over 20,000 liters per minute. So as you can see, or hopefully you can see, these statements are very broad and quite vague. So what is the contractor actually supposed to do with this information? For example, in number 2, the shaft excavation in fine sand and silt at shaft A may require dewatering. Well, will it or will it not? What are they supposed to price? It's unclear. So why were GBRs created? In the 70s, owners tended to say, here's all the geotechnical data, you bid it, you build it. So all the risk was transferred to the contractors. Contractors wanting to win the work sometimes bid the projects optimistically and then filed for differing site conditions or unforeseen condition claims. Litigation on projects began to spiral. It was bad publicity for the owners. It was really ugly for the financials of contractors, and there was this upward trend in litigation. So to stop the litigation, the U.S. industry began producing several research reports. And I say U.S. industry, but this was really done North America wide. And from all the research that was done, engaging not just designers, not just contractors, but owners as well, so kind of all parties involved in underground projects, they came up with a few recommended improvements. So one is a differing site conditions clause in the contract. So for identifying and addressing how differing site conditions will be dealt with during construction. The Geotechnical Baseline Report being part of the contract, and a set of escrow bid documents. So this is essentially a compilation of all the information and a freeze on what the contractor bids on, and having a dispute review board in place to help resolve these disputes. So this publication has evolved over the years. Today, in North America, we typically rely on the ASCE guidelines publication, which was initially called the Gold Book, which was released in the early 2000s, and then a few years ago was evolved into the Platinum Book. So this book, again, was written by essentially a panel from the industry soliciting a lot of feedback and experience from projects. So the updates from the Gold Book to the Platinum Book include things like dealing with progressive contract models, progressive design build, includes decades of experience, feedback from owners, from contractors, from designers, and is largely built on lessons learned to distribute what the best practice should be. It reiterates that a geotechnical baseline report is not a warranty of subsurface conditions, but it should be relied upon by the contractor to define risks and for their bid. So let's get into some of the more details about what a geotechnical baseline report is and what should be included in a baseline report. So really the objective of the geotechnical baseline report is to avoid disputes wherever possible, but also to help resolve claims, ideally without going to litigation, so going to the dispute resolution board. The geotechnical baseline report is meant to serve as the single and contractual interpretation of the ground and groundwater conditions to be encountered during construction. So the focus is what will happen during construction, including both the physical conditions. So this is what is happening that is independent of the construction methods, and also what behavior will be experienced in response to construction. So there has to be an understanding of the means and methods that will be used for the construction of the project, and then how the ground is anticipated to behave in response to those methods. I can't reiterate enough that the baseline report is to focus on the construction conditions and not the design aspects of the jobs. It's not meant to be an input to your design. It's meant to be a baseline for what will be experienced during construction. It's really meant to address that during the work, the contractor claims that something is different. The GBR really answers the question of different from what. So, what sorts of things should get incorporated into the GBR? So everything we talked about in the geotechnical data report, all that geotechnical data that was collected from the project for the project, so your exploration and lab testing program, that goes in to consideration of writing your geotechnical baseline report. But there's also existing conditions that might not be covered by your exploration program. So that may be that kind of known, unknown areas or things you didn't encountered by your site investigation program, but you anticipate to be in the area. Maybe vertical shears, maybe faults, maybe boulders. You only did a drilling program and didn't encounter any boulders, but you know they are in the area. And you're also wanting to incorporate experience and lessons learned from nearby relevant projects. So all those pieces go together into forming the baselines in your geotechnical baseline report. So it's not solely based on the data in your geotechnical data report. And the baseline report is that interpretive report. So it serves as the interpretation. It should have an interpreted subsurface profile. It should have unambiguous descriptions of the properties and behaviors that you anticipate to encounter during construction, and realistic, measurable, observable, and verifiable baselines. So let's get into a little bit more detail on that and how the geotechnical baseline report is structured. So typically, the geotechnical baseline report is written fairly late in the design development process, sometimes near about 90% design development. You can start laying out the structure earlier than that, but you want to have the majority of your investigations concluded by the time you're writing the report, and also have a good understanding of how you anticipate the project to be constructed. The report should also be developed in tandem with the risk registers on your projects. It's not meant to be a very, very long report, typically no longer than 50 pages, maybe on the order of 35 to 50 pages, plus any appended figures and appendices. And in general, the Platinum Book recommends a 1 to 2 page introduction, a few pages on the project description, and the project history, but the bulk of the report is on the ground characterization and construction considerations. It's also important to understand who should be taking responsibility for writing the geotechnical baseline report. So although it's the word geotechnical in the title, it's not solely written by a geotechnical person. They must be prepared by professionals with the right competence and experience. This isn't typically someone who's fresh out of university writing a baseline report. They need to be people who are experienced in the area, experienced with project work, with construction. So, for example, a geologist typically writes the geological history or the regional geology and hydrology section of the GBR. Your geotechnical engineer is leading the section on ground characterization, which is gleaned from the exploration and lab programs. But you should also have construction specialists involved for the construction considerations who have an understanding of the equipment that will be used to build the job, the means and methods, the behavior of the ground in response to those construction means and methods, and other sorts of things that will impact construction, like groundwater, gas, obstructions, contaminations, sensitive facilities in the area. And then the designer or the engineer might be writing the project overview, the references to the contract drawings and specifications, third-party constraints and payment provisions, etc. So what sorts of things should be baselined? If we get into that ground characterization part of the geotechnical baseline report, we're looking into things like the engineering classification of the rock. So the physical characteristics, things like the fracture frequency and orientation, joint conditions, rock mass classification. So the sorts of things that you could perceivably measure during construction and will impact your construction means and methods and the behavior of the ground. If we're talking about soil, we're thinking again about things like the physical characteristics, the thickness of the units, the blow counts, the adjusted SPT values, grain size, percentages, etc. Now, when we're coming up with our baselines, we also want to consider, again, grouping the geology by the behavior and physical characteristics rather than the geological unit. So, for example, this table shows a project where the engineering class is used to define the different units on the project. You can see that there's at the bottom class G. So that pertains to all the bedrock on this project. On this job, the bedrock was all expected to perform in the same way, even though it consisted geologically of a series of sandstones, mudstones, claystones. So geologically separate units, but with similar anticipated engineering behavior, therefore collectively baselined as a single unit. We can also do baselines through histograms to show the distribution of anticipated conditions on the project, or the range of behavior expected, the range of conditions. Now, this baseline doesn't have to be solely based on the data that you have. If you know that your data, or if you expect that your data is different than the conditions that will be experienced during construction, the baseline can be set differently from the distribution of the data. So let's get into a few more specific examples of baselines themselves. So here's an example. A tunnel is to be constructed through weak rock that is anticipated to deteriorate when exposed in the tunnel. So an example of a baseline that might be set around this is the formation is weak, clay-rich, moisture-sensitive, soil-light rock, subject to deterioration upon drying. Now, I'll give you a second. Do you think this is a good baseline or a poor baseline? Hopefully, you've made up your mind for yourself. This is unfortunately a poor baseline. So the issues with this baseline is the subject to. What does that mean? What is subject to measurably? Will it deteriorate upon drying or will it not? What does subject to actually mean? So an improved baseline would be the formation is weak, clay-rich, moisture-sensitive, soil-light rock that will deteriorate upon drying. So even if you think it might not, your baseline should be specific to the behavior that the contractor should anticipate and price. Here's another example. A hard rock tunnel is to be excavated using a TBM through massive rock. So that's the context for the project. Here's the baseline. The tunnel will encounter granite and granodioritic rocks. The uncombined compressive strength of the intact granite may range from 40 to 175 MPa. The UCS of the granodiorite may range from 50 to 250 MPa. Now, again, is this a good baseline or a poor baseline? Can you identify some issues with it? Here, I'll point them out for you. Issues with this baseline are that the may range from 40 to 175 MPa or may range from 50 to 250 MPa. So is it going to range from that or is it not? Also, how much of the tunnel will be in granite versus granodiorite? It's not clear from this baseline. This baseline can be improved with the following. Granite will be encountered for 40% of the length of the tunnel. Then combined compressive strength will range from 40 to 175 MPa with an average of 100 MPa and a range of values as indicated by the histogram in figure X, and refer to that in an attached appendix. You can use a similar baseline for the granodiorite, with it being 60% of the length of the alignment. Now, during construction, there may be a difference from what is encountered, but at least you can measure it from that difference. Let's do one more example. On this project, 10 shear zones are anticipated to be encountered in a tunnel. The shear zone is defined in the GBR glossary. So your geotechnical baseline report can have a glossary of terms, and I highly suggest it does. So here's an example of a poor baseline. Some shear zones may yield up to 100 liters per minute of initial groundwater inflow near the heading, but the flows should dissipate with time. Now, I've already told you this is a poor baseline, but can you identify the issues with it? Some shear zones. What does some mean? And what does should dissipate with time mean? Will it? Will it not? Here's an example of how that can be improved. 10 shear zones are anticipated to be encountered in the tunnel. 3 of the shear zones are anticipated to each yield 100 liters per minute initial inflow to the heading as measured at the station of the TBM grippers. Regardless of the initial inflow, each of these shear zones is anticipated to yield no more than 20 liters per minute after 1 month. So again, that's much more specific, much clearer, and much easier to measure against. So there's words that we should and you shouldn't use when setting baselines. So words I would suggest highly avoiding are may, can, might, up to, could, should, would, some, few, large, significant, local, many, minor, intermittent, continuous. All of these have been subject to issues of claims over the years because they're very hard to measure. It's better to use words such as is, will, and are. So your baseline is meant to set the line in the sand. It's fundamentally a risk allocation tool. So during construction, if the contractor experiences conditions that are within the baseline, that's their risk. That's priced, that should be within their price. There's no claims if the geotechnical conditions experienced during construction are within the baselines. If conditions experienced are beyond the baselines, then it's the owner's risk. So that means that a differing site condition claim might be awarded to the contractor as they weren't expected to anticipate those conditions. Now, you might be thinking to yourself, well, I want the contractor to have all the risk. I'm going to set extremely conservative baselines and the contractor will host all the risk. Well, that you can do that, but if you're doing that and more risk is transferred to the contractor, the price of the project will go up. As I said before, contractors don't accept risk, they price it. So if you put all the risk on the contractor right at the outset by setting extremely conservative baselines, you'll pay for all that risk up front. On the other hand, if you set very optimistic baselines and essentially all the risk is retained with the owner, you'll need to carry much more in terms of provisional sums and contingency to deal with those claims during construction, but the price that the contractor submits upfront will be much lower. So typically we think of this as kind of 3 different buckets of money on a project. There's the known known. So there's what you have a very good understanding of and what you believe is a fair allocation of risk on the project, which is what gets summarized in your geotechnical baseline report. And that's essentially your known knowns or what is in the bid. For certain items that you may expect but not exactly know how much will be encountered, you can agree to set these as provisional sums within the project. So these are things that only get paid if the quantities within the GBR are exceeded, but you have a payment mechanism identified to deal with those items. And then there might also be some really unlikely events or things that you don't anticipate to encounter on the project, but that are contained within your risk register. And those form part of your contingency fund. So those are only paid if the conditions are encountered. So the budget for your project isn't just this known knowns bucket or what is in the bid, is actually your what is in the bid plus your allowance for provisional sums plus what is kept in your contingency. So we're nearing the end of the presentation. So just to conclude and reiterate what the difference between a geotechnical data report versus a geotechnical baseline report is. Your geotechnical data report contains all the factual information that you obtain for your project, from field exploration, from laboratory testing, from past projects in the area. So it includes things like your boring logs, your lab testing your results, your in situ testing results, photos of your rock core soil samples. But again, no interpretation, just the data. The geotechnical baseline report is your single contractual interpretation of the anticipated subsurface conditions. So it is what sets the line in the sand, explicitly telling the contractor what will be encountered during construction, both in terms of the physical baselines, so the intrinsic properties of the ground, and also the behavioral baseline, so how the ground will behave during construction. And that geotechnical baseline report takes precedent over the geotechnical data report within the hierarchy of the contract documents. So I want to thank you so much for having me. I really appreciated being able to provide this presentation on behalf of the CUIIC, and I think we have some time for questions.
Thank you, Dani. Very informative presentation. So there are some questions. I'm just going to dive into it. The first one is asking, from the example section, do you have any experience you can speak to regarding ways that owners and engineers manage their risk if there are changes in actual conditions that results in cost delays and design changes?
Sorry, just let me read the question one more time. So do you have any experience of how owners and engineers can manage their risk if there are changes in actual conditions that result in cost delays, changes, etc., design changes, etc.? So if there are differing site conditions that are experienced during construction, what I've seen on the owner and engineer side of things is making sure that the right information is collected to identify and quantify what that differing site condition is. So it depends on if it's related to something that was a baseline in the document. So for example, say there was a baseline that said you will encounter one boulder in your excavation, and instead the contractor encountered 10 boulders during excavation. That's a pretty clear differing site condition. And typically the owner would pay the contractor for that differing site condition. Now, it can become more complicated if something is encountered that wasn't within the baselines at all. So there is a project I know about where they encountered arsenic in some of the excavated material, and it wasn't baselined anywhere that there would be any arsenic. It resulted in additional treatment costs for the contractor. They went back to, so if it isn't within the baseline report, you go back to the geotechnical data report to see if there's anything within the data report that supports that, so that the contractor should be reasonably aware to anticipate those conditions, and that can be used to help adjudicate the claim. So hopefully that provides some answer to that question.
Yes, so there are so many questions. I'm going to quickly dive into some again. Okay. What is the difference between GIR, Geotechnical Interpretation Report, and GBR?
So typically a geotechnical interpretation report is not a contractual document. So that might be used by the design team to inform the design, but it's not part of the contract document. So it's more an interpretation of the data that's relied upon for design.
Okay. Which stakeholder pay for GBR? Is it owner, contractor, management team?
So that would depend on the type of contractual model that you're going with. But if we talk about a typical design bid build project where the owner is paying a designer to progress a design to 100%, that design is then tendered for a construction contractor to bid on, who then builds the project, it would be the owner paying the designer to develop the geotechnical baseline report. In progressive design build, for example, the geotechnical baseline report might be developed collaboratively, so between the owner, their designer, and the construction contractor.
Next one is around what's your advice on getting owners to accept that the baseline statements belong to them and are their risk to share with contractors?
That's a great question. So I think it comes down to educating owners on the use of geotechnical baseline reports. I mean, it is typical in underground construction projects that the owner owns the ground, and that through a well-written geotechnical baseline report, you can appropriately share the risk on the project. So it's helping owners understand this, getting in to talk to them early. I've found connecting them with other owners that have experience. So I've done a lot of work over the years with Metro Vancouver and Vancouver, BC, and that's a very well-educated owner on the use of geotechnical baseline reports. So that can help sometimes as well.
Next one is around does the GBR ever do more site investigation or just use what is already done?
So the GBR should never be presenting new data. It's not meant to be a data report. If there is additional data done between the kind of development of the geotechnical data report and the GBR, that data should be part of the geotechnical data report. And anything that's used to facilitate the baselines is what gets summarized in the baseline report.
And the next one is a little bit technical. They're asking about, could you provide best practice perspective regarding when it's appropriate to provide earth pressure diagrams in GBR?
When it's appropriate to provide earth pressure diagrams in the GBR. I mean, my perspective on that is the earth pressure diagram something that you can measure during construction? Is it something that's a behavior or an intrinsic property of the ground? It seems to me, or in my experience, your earth pressure diagram is more so an input to your design than to something the construction contractor is going to experience during construction. So I would suggest it's more appropriately found in your geotechnical interpretive report.
The question is around how does the GBR deal with unknown ground condition between the borehole logs?
Great question. So unknown conditions between borehole logs, that's subject to the interpretation that the baseline report is meant to cover. So you are doing an interpretation of what that is and putting assumptions behind that, knowing that what you are assuming might not be correct, but you are telling the contractor essentially what their bid should be based on. So an anticipated conditions between those two locations.
The next one is around, are GBRs required by law in Canada?
Not as far as I'm aware. No, they're more an industry best practice rather than a legal requirement.
Okay. GBRs are usually used for larger projects. Where do you put the cutoff to have a GBR for tunneling, macro tunneling for the project?
That's a really good question. And I think the answer, as most things in geological engineering, is it depends. I think it depends on the risk profile for the project and the general understanding of the ground conditions. So if you have, say, a micro tunneling project in an area where the geology is very consistent, you're working with fairly well-known means and methods, a GBR might not actually be necessary because the risk of encountering unforeseen conditions or differing site conditions is quite low. So if those are the conditions and you're not anticipating something that might be different during construction, you might not actually need a geotechnical baseline report.
Thank you, Dani. Next one is, are provisional costs regulated by law in Canada?
Again, I don't believe there is a legal requirement for this. It's more on a contract-to-contract basis and something agreed with the owner in terms of the best way to handle provisional sums on the project.
Okay. GBR is used to prepare design to give the parameters. So how could you prepare the GBR at 90% design?
So I would argue that that is not the correct use of a GBR. The GBR shouldn't be used to develop the design parameters. The Geotechnical Baseline Report is the contractual understanding of what conditions will be experienced during construction, and inputs for design can be separate from the baseline report.
Should GBRs be sealed by engineers? Is not really an engineering document, and doing so may encourage owners to claim against the engineers where there are claims.
So my understanding on this side of things, and again, I worked in BC longer than I've worked in Alberta, so I'm more familiar with the EGBC regulations, but any document that is prepared by a professional engineer and is to be relied upon by someone else has to be signed and sealed. Therefore, a geotechnical baseline report would fall into that category and required to be signed and sealed by the professional engineer. But again, as I said, a geotechnical baseline report is not a warranty that those conditions will be encountered. So it's more meant to be the contractual baseline, not a guarantee that those conditions are what will happen.
I remember some GBRs indicating how many cobbles or boulders will be encountered during tunneling. How do the authors of GBR make such a call? What evidence will they rely on to make those statements?
So cobbles and boulders, again, challenging to baseline, but typically, depending on how deep the layer is that you're looking for, you might be able to get some information on the frequency of cobbles and boulders from test pits. You might be able to get information on it from past nearby excavations or nearby construction experience. But it depends what data is available for your project and what into how you can kind of decide what the appropriate baseline is.
Thank you. You mentioned that GDR is data only and GBR focuses on construction condition. Where in your framework do the interpreted design parameters for design belong?
So that would be in that geotechnical interpretive report, which would be not a contractual document. So when we're talking about data reports and baseline reports, we're talking about contractual documents, but design reports would fall outside of that.
Another question, thoughts regarding providing interpretive items like RMR in GBRs? This seems to be still a highly discussed item among GBR authors.
Yeah, it's a good question. And I think there is some debate among the industry of which specific behavioral parameters should be included. I think the most important ones to include are ones that impact the ability to understand the behavior of the ground, or that would impact the selection of the construction means and methods. So, and that are measurable during construction as well. So I've typically seen like fracture frequency or rock quality designation baselined along with things like uncombined compressive strength, abrasivity.
Thank you. Maybe the one last questions, Dani. What is your experience with arbitrators' interpretation acceptance of GBRs in dispute resolutions?
I don't have that much experience on that, so I probably can't comment. Typically, like the suggestion from the Platinum Book and from others is to have a dispute resolution board set up to do its best to handle dispute resolutions before it going to litigation, and that dispute resolution board is typically set up by as like one expert in kind of the conditions appointed by the owner, a second one appointed by the contractor team, and then a third jointly agreed by the previous two. So kind of a three-person team that helps review the differing site conditions. And then if that can't come to resolution, that's when it goes to arbitration and litigation.
Awesome. So there are so many other questions. I apologize. We are getting to 12 o'clock Mountain Time. So I want to thank again. First of all, thank you all for attending the webinars, and thank you, Dani, for the informative presentation and answering all the questions. We appreciate that. Before we end, I want to thank as well all the QIC members. There's close to 90 organizations that are part of the QIC. Without their support, all these educational and research activities happening wouldn't be possible. With that, we conclude this webinar. Thank you again. Looking forward to see you in future QIC events.
Thanks, everyone.